Imagine a world where information travels not in bits and bytes, but through the very fabric of reality itself. Imagine a future where instantaneous communication transcends the limitations of space and time. This is the tantalizing promise of quantum teleportation, a revolutionary technology poised to reshape our understanding of the cosmos and redefine the boundaries of human ingenuity. For centuries, the idea of teleportation has captivated our imaginations, fueling countless science fiction narratives and inspiring dreams of a world where the constraints of distance are effortlessly overcome. Today, on the cusp of a new scientific era, we stand at the precipice of transforming this once fantastical notion into a tangible reality. Quantum teleportation, however, is not about the physical transportation of matter as often depicted in science fiction. Rather, it involves the instantaneous transfer of quantum information, the properties and states of subatomic particles, from one location to another regardless of the distance separating them. This groundbreaking feat is made possible by the mind-boggling phenomenon of quantum entanglement. Like a cosmic dance across the vast expanse of the universe, entanglement links two or more particles in a profoundly intimate way. Their fates become intertwined, their destinies forever linked, even when separated by vast cosmic distances. Through this enigmatic connection, the manipulation of one entangled particle instantaneously affects its counterparts, no matter how far apart they may be. Quantum teleportation, once relegated to the realm of science fiction, is rapidly becoming a scientific reality. This groundbreaking technology is not just a figment of our imagination, but a testament to the incredible advancements in quantum physics. It's a testament to the power of human curiosity, the relentless drive to push the boundaries of what we know and explore the unknown. Our relentless drive to explore the universe's deepest mysteries has led us to this point, where the lines between science fiction and reality blur. The implications of this technology are as profound as they are far-reaching, promising to revolutionize fields as diverse as communication, computing, and our very understanding of the cosmos. Imagine a world where information can be transmitted instantaneously across vast distances, where quantum computers solve problems that are currently unsolvable, and where our grasp of the universe's fundamental laws is transformed. To grasp the principles underpinning quantum teleportation, we must first venture into the bizarre and counterintuitive world of quantum mechanics. This realm, governed by laws that defy our everyday intuition, is where particles can exist in multiple states simultaneously, a concept known as superposition. This realm, governed by laws that defy our everyday intuition, is where particles can exist in multiple states simultaneously, and where the act of observation itself can alter the very fabric of reality. In this strange world, particles can exist in multiple states simultaneously, a phenomenon that challenges our classical understanding of reality. Here, information can travel faster than the speed of light, defying the limits set by Einstein's theory of relativity, and where the act of observation itself can alter the very fabric of reality, a concept that has puzzled scientists for decades. At the heart of quantum teleportation lies the mind-bending concept of quantum entanglement, a phenomenon that Albert Einstein famously dubbed spooky action at a distance. This phenomenon, famously dubbed spooky action at a distance by Albert Einstein, describes the bizarre connection that can exist between two or more quantum particles. It describes the bizarre connection that can exist between two or more quantum particles, where the state of one particle is instantaneously correlated with the state of another, no matter the distance between them. These particles, once entangled, share a destiny, their fates intertwined regardless of the physical distance separating them. Their fates intertwined regardless of the physical distance separating them, creating a connection that transcends our conventional understanding of space and time. Imagine two coins flipped simultaneously, one landing on heads, the other on tails. In the everyday world, these outcomes are independent, unrelated events. But in the quantum world, entangled particles behave more like two sides of the same coin. In the quantum world, entangled particles behave more like two sides of the same coin, where measuring the state of one instantly reveals the state of the other. Measuring the state of one instantly reveals the state of the other, no matter how far apart they may be. This instantaneous connection defies our classical understanding of the universe, opening up new possibilities for communication and computation. Quantum entanglement is not merely a theoretical curiosity, it's a fundamental phenomenon that challenges our understanding of reality. It's the very engine that drives quantum teleportation, a process that seems almost magical but is grounded in the principles of quantum mechanics. It's the invisible thread that connects particles across vast distances, enabling the instantaneous transfer of quantum information, defying the classical notion that nothing can travel faster than light. To understand how this works, we need to delve a little deeper into the quantum realm, where the rules of classical physics no longer apply. Imagine you have two entangled particles. Let's call them Alice's particle and Bob's particle. These particles are mysteriously linked no matter how far apart they are. These particles are in a superposition of states, meaning they exist in multiple states simultaneously until measured. This is a core concept of quantum mechanics. It's like a coin spinning in the air, both heads and tails at the same time, until it finally lands. Only when we observe it does it choose a definite state. Now let's say we want to teleport the quantum state of a third particle, Charlie's particle, to Bob's particle. This process is known as quantum teleportation. This doesn't involve physically moving Charlie's particle from one place to another. Instead, we use the principles of quantum mechanics to achieve this feat. Instead, we use entanglement as a resource, a kind of quantum link that allows us to transfer information instantaneously. First, we perform a joint measurement on Charlie's particle and Alice's particle. This step is crucial for the teleportation process. This measurement doesn't reveal the individual states of the particles, but rather their relationship to each other, which is key to the next step. This information is then sent through a classical channel, like a phone call or internet connection, to Bob. This step ensures that the information is communicated accurately. Here's where entanglement works its magic. The measurement on Alice's particle affects Bob's particle instantaneously. Because Bob's particle is entangled with Alice's particle, the measurement performed on Alice's particle instantly affects the state of Bob's particle, and no matter the distance. By applying a specific transformation to Bob's particle based on the information received from Alice, Bob can reconstruct the exact quantum state of Charlie's particle, completing the teleportation process. The theoretical framework for quantum teleportation was first laid out in a groundbreaking 1993 research paper. This paper, authored by a team of physicists including Charles Bennett and Gilles Brassard, introduced the concept of entanglement-based teleportation, which relies on the peculiar properties of quantum entanglement to transfer information instantaneously. However, it wasn't until 1997 that scientists successfully demonstrated this phenomenon in a laboratory setting. This initial success was a monumental step forward, providing the first experimental evidence that quantum teleportation was not just a theoretical construct, but a feasible process. Using photons, the fundamental particles of light, researchers at the University of Innsbruck in Austria successfully teleported the quantum state of one photon to another over a distance of about 1 meter. This experiment utilized a process known as quantum entanglement, where two particles become interconnected in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. This landmark experiment marked a pivotal moment in the history of quantum technology, proving that quantum teleportation was not just a theoretical possibility, but a tangible reality. The success of this experiment ignited a wave of research and experimentation in the field, with scientists around the world striving to replicate and build upon these initial findings. Since then, scientists have been pushing the boundaries of this technology, teleporting quantum information over increasingly longer distances and between different types of particles. These advancements have not only deepened our understanding of quantum mechanics, but have also paved the way for practical applications in secure communication and quantum computing. In 2017, a team of Chinese scientists achieved a groundbreaking feat, teleporting the quantum states of photons from a ground station to a satellite orbiting over 1,200 kilometers above Earth. This experiment, conducted by the Michio satellite team, demonstrated the potential for quantum teleportation to be used in space-based communication networks, offering unprecedented levels of security and efficiency. This remarkable achievement shattered previous distance records for quantum teleportation and opened up exciting possibilities for space-based quantum communication networks. The success of this experiment has inspired further research into the integration of quantum technologies with existing communication infrastructures, potentially revolutionizing the way we transmit information across the globe. Beyond photons, researchers have also made significant strides in teleporting quantum information between atoms, the building blocks of matter. These experiments have demonstrated that quantum teleportation is not limited to light particles but can also be applied to more complex systems, opening up new avenues for research and application. In 2014, scientists at the University of Science and Technology of China successfully teleported the quantum state of one rubidium atom to another over a distance of 3 meters. This experiment showcased the versatility of quantum teleportation and its potential to be used with different types of particles, further expanding the horizons of this groundbreaking technology. These achievements represent major milestones on the path to practical quantum teleportation technologies, bringing us closer to a future where information can be transmitted instantaneously across vast distances. This revolutionary capability has the potential to transform communication, computing, and our understanding of the universe itself, heralding a new era of technological advancement and scientific discovery.